Good afternoon, everybody. Welcome to today's webinar hosted by us here at the Nuclear Industry Association. I'm Iolo James, the NIA's Head of Communications. So we have something a little different from our normal webinars today. We're going to get a live tour of the facilities of UK Atomics and its parent company, Copenhagen Atomics. Live from the Copenhagen Atomics Development Centre and factory located within Alpha Level's Innovation House in Copenhagen from Denmark. We have one of the founders and chairman of the company, Thomas Jan Pedersen, alongside Managing Director of UK Atomics, Michael Drury. And in this live stream, we're going to see up close what the team have been doing and the product development-led approach to technology progression. And if we're lucky, we might get to see some prototypes as well. But don't let me spoil the surprise, of course. There is some housekeeping before we begin, and please can everybody turn off their microphones and mute yourselves so we don't have any unwanted background noise. We are recording the session, so please turn off your cameras if you don't want to appear in that. We'll have a little time for a Q&A at the end as well. So please, if you have any questions, and I'm sure you will, use the chat function to submit those questions. So without any further ado, let's get going then and let Thomas and Mike tell you about how targeting £20 per megawatt hour can force a rethink in nuclear's role in the energy system and how it could support our own British security of supply and net zero targets for decarbonisation. Over to you, Mike.
Hour. And I think the challenge that we've got is much bigger than just the technology itself. There's a whole load of regulatory process, a whole load of site licensing, siting applications, development, etc. But a big focus for us is product-led development, right? So maybe the best thing to do is let's just show everyone a quick presentation, talk you through what we do and our approach. Yeah, let's do that. Okay, so welcome everybody. We are really focused heavily on changing how we do the energy mix, how our approach to the market is entirely different to anybody else. So we are genuinely looking for a paradigm shift in how we supply nuclear technology to the global energy mix. So with that in mind, you know, we're not just focused on maybe a grid application or an industrial application. Of course, we provide for those, but it's not just one plant that'll do that. It is by mass manufacturing of our plants, our thorium reactors, that we're able to produce reactors effectively similar to a car production line, right? So we're trying to have multiple reactors in 40-foot ISO containers coming off a production line, not at one a year, but how many are you looking to do per year?
At least one per day.
At least one per day. So if we go at the market size, we're looking at tens of thousands of reactors that we're trying to move towards. So with that in mind, we have to look at the technology itself. There's a lot of history in the technology, right? It started in development with Weinberg in 1950. So it's not just us that's developed the tech from core first principles, really. There's a host of development that was done back in the 50s when they looked at the original concept of the technology. But we're also looking at thorium as the fuel salt. Why are we looking at thorium, Thomas?
Well, because thorium has some great advantages, especially when you build a molten salt reactor in thermal spectrum. You can actually that's the only way you can make a breeder reactor is by combining molten salts and thorium. There's no other way to do it in thermal spectrum. So it has some advantages.
And the thorium at the moment, right? If we do rare earth metals and the mining of those rare earth metals, at the moment, that thorium is just waste material that's thrown back in, right?
Yeah, we do a lot of mining around the world for other materials, whereas thorium comes out of the ground and it's not being used today. So essentially, they just put it back in the ground.
Yeah, so it's a good, cheap, readily available resource. So it makes sense to use it. Founders, it's not just you on your own. You're one of the founders, aren't you? Maybe you could introduce the others.
Yeah, so we were 4 guys starting the company back in 2014, 3 engineers and a physicist, and we're still working really hard every day to make this happen and bring this technology to the market.
So this facility was just the four of you to start with, or?
Yeah, so when we moved in here at Alpha Laval, that was back in 2019, we were 5 people. Now we are 60 people here, and we are actually sort of maxed out. We need to move to a new location later this year.
But we're not telling anyone about that yet.
Oh.
Well, maybe we just did. Okay, so the approach that we're looking at is a multiple reactor concept. So we basically take our reactors and we put them together a bit like a Lego bricks, and then build on from those. So depending on what size you want, we can have a 1 gigawatt plant, or we can use that 1 gigawatt, and you can see we can be scalable and flexible to meet the size and scale of the demand. So effectively, if you want just one for an industrial application on a smaller scale, we could do that. If you want hundreds for a large industrial application, maybe like ammonia production or hydrogen production, then you might have 200 or 300 of the reactors. Or if you wanted a grid application, it might be, say, 25 reactors that are coming together. So we have a very high power density ratio, which allows us to get our efficiency quite high. And we might tell you a few things about our design as we go through, and you'll understand why we can be a little bit more efficient than most, because really targeting that $20 per megawatt hour is a challenge. But in that challenge, we're not just looking at supplying for synthetic fuels or supplying energy for hydrogen production or desalinization or grid application, but actually the technology we're working on, as you were saying, as a breeder reactor, we're also looking at, well, can we get rid of the waste? Everyone always talks about the waste, right? But actually, if you design your technology right, you can use the waste. It can be an asset. And in the UK, we've got 140 ton of stockpile material. Effectively, that costs us around about 73 million per annum in storage costs, 50 billion per annum for the total cost to get rid of it. So there's a huge cost for just maintaining what's called a liability in the UK, but actually we could call it an asset in the UK. We could produce 30 gigawatts of electricity over 50 years, which effectively gives us 780 billion of value to the UK taxpayer, to the UK economy. So if you design your reactor right, you can take advantage of that. And the way that we've been designing our reactors is, I'd argue and say it's not different, really, because in the original days, this is how technology was developed. And if you look at any other market, whether it be automotive, aviation, even software, it's all check the development, the stage of that development, reassess, does it change the design? If it does, engineer it again, test and develop it. Does it change, redesign, test and develop? It's an agile process. That's not new. We've done it for years in automotive and aviation, right? So in our technology, or in our company, and the approach that we're taking, it's very much a product-led design. We're not just doing a design on paper and taking it to the regulator and going through it. Of course, we design to the regulatory standards. Of course, we have to. But we're definitely going through at every single stage how we develop those products. And each bit of those products, we've then commercialized. So, you'll see some of these things. And as we go through, you'll see that we've got a prototype reactor that you'll see right there now. We'll have to have a criticality test by 2025, which will be our research reactor, our molten salt demo, for want of a better description. And we'll have our commercial reactor at the end of that, right, where we can get full scale. That's what we're doing. So if you look at our timeline for that, then we've got several stages of development that need to be done. Right now, we've looked at water, and we'll explain why we've looked at water a bit later. But the next stage is to go into the salts, the FLENAC, the thorium-based salts, and then eventually onto that criticality experiment that I've been talking about for 2025, which is why we're looking at the UK. Because effectively, the UK has a good regulatory understanding, has lots of capability within nuclear, has steel production, which works with our technology. We use potentially a lot of steel. So that's good, because we don't have steel production in Denmark, and we don't have a regulator in Denmark that can take us through licensing. So actually access to things like site license, sites that already have nuclear, to resources, people, material, places, etc. There's a big benefit to working between the UK and Denmark, and two of us have been working quite closely on energy already. So it's not something new. The relationship between the UK and Denmark is already pretty strong. And so for us, we're looking to get to our technology readiness level by 2028, which everybody will argue for molten salts. 2028, really? Well, maybe we can actually show them. Maybe we'll show them some of the things that we've done. We've got 60 odd people. We started 2014 with 5. Yeah. Now we've got 60. That's not that far away. And when you look at our facilities, we've got a factory over there that we're growing out of now, that we need to find somewhere new, which Thomas might have just told you about. We've got some technologies that we've developed. We deliberately designed these technologies to be open and available for collaboration, right? So an example of this is the open source modeling, the reactor physics modeling that we do. That resource is available on GitHub, so people can look at what we've done and they can contribute to the development of it, right? Yes. So if you look at the approach that we take on every technology, whether it be the electronics that we look at, and we'll go through and you'll see some of these products that you can see on the screen now. Those electronics, we've worked with manufacturers. If you look at the pumps and how they're developed, at the top you'll see some of the early stage pumps, and at the bottom you see a very specialist pump that again we'll talk you through a little bit later. And we also have to make things like the salt. So as we develop some of those kind of technologies, we have problems such as maybe corrosion, right? And one of the key contributing factors is the purity level of the salt. So what does that mean we have to do? Well, we have to buy the salt, but it's not that easy to buy it at that purity level, is it? So we end up having to manufacture the salts. And all of these products that we do, you can see our testing there. You'll physically see these in a second, actually. So maybe we ought to stop looking at all the different products that we have, and maybe we ought to just jump straight into looking at maybe the prototype that's out there, some of the actual products. And you guys that you've seen the screen flicking through, you'll have seen there's lots of products that we've quickly shown you. You'll get a copy of the presentation anyway, but the real thing, let's go and have a look at it, shall we?
Yeah.
Okay, so just bear with us a second as we transition from one camera to the other, and you'll see it's a little bit more rough and ready now, and a bit live as we go and have a look. Let's physically look at things, shall we? So what's this, Thomas?
So this is the first stop. This is the reason why we're here. Alfa Laval is the leading manufacturer of stainless steel plate heat exchangers in the world. They are actually manufactured only 50 kilometers away from here. This is an example of the size of plate heat exchanger that would be in our commercial reactor. There would be 7 of these in a commercial reactor. We're already testing these here at the current site.
You're already testing the heat exchanger in a molten salt environment, though.
Yes. So Alfa Laval didn't have the capabilities of testing at high temperatures with molten salt, corrosive molten salt. So we're doing testing with fluoride and fluoride salt at high temperatures. We have still not managed to do tests with the radioactive salts, but that's coming.
Great. Well, shall we have a look at some of the electronics? So there's quite an array of electronics here. Talk us through. How did you get to? I presume these are all just straight from the manufacturer, right?
Yeah. So we've developed all these different sensors and electronics and control systems ourselves over the years. And in the beginning, we were using commercial available components, but one or the other didn't fit with our needs, and then we developed our own. So basically, we design the electronics here. We have it manufactured by sub-suppliers. It come back here, and then we assemble and test it here to make sure that it's all according to spec. And for example, here is this is a sensor for measuring humidity in the argon gases. And you can see the electronics that is inside one of those humidity sensors here. It's all our own design. Here's another example of another sensor. This is a oxygen sensor. Actually, these sensors here are inside a commercial product, which we were using originally, but then we had decided to design our own version because the electronics in here is better at controlling the temperature of these according to the mix of the gas. So
these two sensors were two different sensors from the same manufacturer.
Yeah. Yes.
And they couldn't provide you with the box that basically links it.
They have another box, but it's not as accurate as this one. So we've improved it by creating our own box. There's also a humidity sensor in here to calibrate everything together.
And then with that sensor, then have you gone back to the manufacturers and worked with them, or?
Yeah, we have an ongoing dialogue with the manufacturer also to see if we can get it even further down. So this one is capable of measuring down to 5 ppm of oxygen in a hot gas, which is very, very low. But of course, in the future, we might want to get even further down.
And I see that you've got a pi hat here, several pi hats here. Isn't there a link with that in the UK?
Yeah, that's a very proud UK product, the Raspberry Pi.
Yeah.
And also the CPU that sits in here is a 4-core, 64-bit ARM CPU. So the ARM CPUs are the same that are in your phone, and they are developed in the UK, and they are really, really good for this application.
So we've already, in our own products and what we're doing, we've already got a UK-Denmark collaboration going on.
True.
Cool. And all of these products, you've got stacks of them on the side there, and the cases that we're doing. We make our own cases and how we bring it all together and the software integration for it. I presume that it takes a while to test and develop all of these.
Yeah, we've spent a lot of resources on test and development. The guys are sitting just over here doing the software development for all of these boards. All of these boards have a small 32-bit CPU inside of them, and they can all communicate. We will talk about that a little bit later. We also have over here some of the production.
Some of the 3D printers as well?
Yeah, so it's today it's very easy to do 3D printing of boxes like that. You saw it before. So we just print those on 3D printers. They are running basically day and night to keep up. And
24 hours a day.
Yeah. And
I see we've got lots of different colors as well.
Yes.
It's a stack of different things.
And over here we have the testing systems for testing and calibrating the different types of sensors. And over here behind me we have the electronics.
Yeah.
So this is a place where we can do a little bit of a rework or testing or debugging of the electronics.
So we do the software in the loop testing, and we can do the hardware in the loop testing all here where we are today.
It's actually very efficient to have our own.
But none of this was here in 2014, was it?
No. We've all created all of this since 2014.
Wow. Well, look, this looks like an easy setup, really. I think maybe we should have a look at the actual factory.
Let's
go over to the factory. So we're just going to walk across to the factory now, and as we go over there, there's going to be a dead spot. So you might find, as we walk through the big concrete staircase, that they can't hear us or anything. So we'll stop when we get to the concrete staircase. You know, the factory that we're moving into here, how did you come about to being part of Alfa Laval here? I mean, it's a big place, isn't it?
So Alfa Laval, this is the Alfa Laval headquarters.
You might want to just stop for a second there, Thomas.
Yeah, hopefully the sound.
Hopefully you got sound again.
So this is all the buildings here at this site. It's the Alfa Laval headquarters in Copenhagen. They have 600 employees work here. They make a lot of different systems here, but predominantly food and water related systems. Actually coming up from the test system here for desalination of seawater. We're also working with them because, of course, waste heat from molten reactors are very important for desalination of seawater to get fresh water for human consumption and for crops, producing crops, and also for hydrogen production. So the partnership with Alfa Laval is actually a good relationship for the type of applications as well that we could apply to as well. So not just the heat exchangers and that side of it, but actually desalinization, ammonia production, hydrogen production. That's their kind of core market too, right? Yes, and it's been a great opportunity for us to be here at Alfa Laval and have our offices and our workshops here for almost 5 years now.
Great. So this is our first bits of equipment. Tell us about what are we looking at?
All of our test tubes where we have static salt test. That means the salt are molded inside of here, and it just sits there statically molded for several months to do corrosion tests, to do testing of compatibility between the salts and materials and gaskets and sensors, and we try at different temperatures, different purity levels, different humidity levels.
And you bought this equipment from somebody else, right?
No, so we developed all this equipment about 4 years ago.
Right.
It's actually, there's been several.
So that's one of our components. So when you do the static testing, have you encountered problems or seen any failures as you go through? And can you tell the audience?
So,
can we have a look at some of those?
Yeah.
Yeah.
Okay. So this is an example of one of the tubes that are inside the static test system. So you normally have salt in here in the last part that are molten, and this sits there molten, and then you can test different materials. This is not a steel, this is a carbon composite pipe, and down here we have stainless steel flanges, gaskets, and of course you can test the different types of salt.
So everyone always talks about in molten salt reactors that you get a lot of corrosion, you've got a lot of failure due to corrosion. And I can see there's definitely one that's corroded there. What's that? Tell us about
that. There was a gasket down here that leaked, and then because it leaked, then when we took it out of the system, then it starts corroding from moisture in the air. And you can see the stainless steel is not very stainless anymore. And this one here is stainless steel pipe, and it's the same stainless steel flanges. And the salt inside that was used for this test is a fluoride salt.
Yeah. So if we take that salt, how do we stop the corrosion from happening then?
If you make sure that there is no oxygen and no moisture, then you can really make a small amount of corrosion, and then you remove other impurities, then you get the corrosion down to 100%.
And we were able to buy that salt in the market. I might keep asking these questions, guys.
Yeah, so it's for example, these salts, when you buy them, they are full of moisture, and you have to clean them or evaporate the moisture. There's different people around the world that they've been experimenting with this and optimizing this process. But we've worked on this for many decades because we started at the university 10 years ago, and we are really, really good at purified salt to put megatons. We are selling those.
So we make what, a couple of kilograms?
We now have a production line that makes roughly 1 ton of these purified salt per month.
Wow.
And when we move to the new facility, we will start to make many tons. So we've got a whole host of loops that we've got here that are walking past now.
Maybe, Thomas, you can talk to us about this first loop. What's this?
Yeah, so this is an example of what is inside what we call a test loop. It's a system for pumping salt around and around. You can see the pipes here where the salt is pumped around. This is a storage tank of the salt, and basically the testing here is to pump the salt around and around and around for many hours or many months, and then test all the different equipments in here. There are filters and valves and reheaters and other valves and flow sensors and pumps and many different types of sensors in there.
And you can see some of the components, the flanges that we had tested over there. You can see being tested here. And again, is this just for us, or are we doing this in collaboration with others?
We started this development just for our own, but of course we want to help this industry get going sooner rather than later. So we're collaborating with a lot of universities and national labs around the world. So we're actually selling these test systems to other universities and national labs around the world.
In the UK?
Also in the UK. Leeds, for example, Leeds University has bought one of these loops. This one, for example, is going to MIT in the US. So this part here is the furnace where everything gets really hot, 600 or 700 degrees. And then there's a cold part over here where we have all the electronics and sensors.
And there's quite a few different loops that we've got in place here and maybe around the world as well. I presume then that we collaborate with them to get the test data and improve. So how many hours of test have you got now?
Again, I can't remember the exact number, but more than 100,000 hours of testing on all these different systems.
Right.
and of course the groups at universities and national labs around the world that work on this, they also contribute to that amount of
So a
testing.
bit like the open source MCs.
Yeah, you can say it's a collaboration. Not everything is open, but we try to share as much as we can.
To improve the community.
Exactly.
And do other Reactor vendors?
Yeah,
do that as well?
there is a
Or
few
just-
Reactor vendors that we work with, some of the, you can call it competitors.
Yeah.
The way we look at that is until we have reactors that are producing commercial reactors, we're not really competitors. We are all in the same boat. We need to get this industry moving. So we don't see it as competitors. Essentially, we're collaborating with.
Well, I see on there we have a pump that we were developing. See that you've got the special pump, which I didn't say the name, the electromagnetic bearing pump.
Yeah.
But maybe you can tell the audience a bit about that.
Yeah, so this is the latest version of the pump. It's got electromagnetic bearings, and that means that everything that is rotating inside here is levitating on a magnetic field. Nothing is touching each other, and that means that it can run for many days or years without degrading. So we expect that this one can run at 600 degrees inside a reactor for 10 years.
And let me guess, we went to manufacturer and they provided us with a pump.
No, we also have to develop that ourselves because there's nobody else in the whole world that are developing high temperature AMD pumps. So we're the first ones to do that. And we are collaborating with some of the global pump manufacturers, but this design is our own design. We've patented it and we're making these.
And I guess we're now looking, I mean, these are quite small scale loops. We have to scale it up though, right?
Yeah. So this one here is big enough for a 1 megawatt reactor. But
so what size is that in comparison to the full commercial?
Yeah, so the commercial reactor, the pump for that is 100 times more heavy, and also bigger, of course, much bigger.
And again, just on the loops that we've got here, we have to scale the loops themselves, right? So maybe we should show them the prototype loop.
Yeah, let's go on.
So this bit, we've got a few bits of the loop that we're going to see is maybe hidden from view, but we'll see if we can convince Thomas to do some sneak peeks some of the areas you might tell me later. Let's go through it. So Thomas, tell us about 6.0.
So this here is a test platform for sort of before we start to make reactors, and it's the same size as a test reactor. And it has all the same things: a reactor core, heat exchangers, the pumps, all the sensors and everything. And we use this as a test platform to test that everything is working before we move on to salt testing.
Can we have a look a bit closer?
Yeah, let's go.
Yeah, let's have a look a bit closer.
Okay. Yeah. Yes. So
we've got different parts to it, right? So let's say we've got reactor core, we've got the thermal insulation, and then we've got the non-nuclear side of it.
Yeah.
Just maybe take us through the section.
So if this was a real reactor, this would be the reactor core. And then this section here is hot, like it would be 600 degrees. And then on the other side of the insulation wall, 25 degrees. And all these pipes here is where the salt would be running inside. The size of everything here is for a 1 megawatt reactor.
And we can see some of those pumps.
Yeah, if you come over here.
So some of these pumps into the early stage development.
Yeah, this is the first version of the pump. So yeah, this is a more simple pump. It cannot run for 10 years, but it's a very good test platform for us to do all the testing we need to do. And you can see over here the water is running in the pipes, coming through the reactor core and going around and around. So
you can see it's smaller scale.
Yeah, the heat exchangers over there. Those are alpha level heat exchangers.
If you look at the parts of the kind of thermal barriers up the top there, you can see the pi hat. So we talked earlier about the bank of pi hats that you have.
Yeah, so those computers up there are coupled, so they all calculate the same again and again and again. And then they vote on the result 10 times a second. They vote to make sure that they agree on what's going to happen next. Should we turn the temperature up or down, or turn the pumps up or down?
This is only half the scale. Another reactor over there.
Yeah, let's go and have a look at that.
So we were just moving from a 20-foot ISO container with our prototype 6.0 water testing, looking at what drain downs, all sorts of different things for simulants. How are we using water instead of salt?
It's because it's a lot cheaper to do testing and changes and more testing and development on water. And when we have to heat up to 600 degrees, the reactor takes several weeks. So if we make a mistake and have to change the software or something, it's too expensive to test on that before we know that it works on water.
And water is representative of salt?
Yeah, so water have the same viscosity as the salt, but the density of the salts are typically 4 times higher than water.
Okay, cool. So on the outside of this, we've got a cooling station.
Yes.
Why have we not got that on the water one?
The water one is just running at room temperature, but the salt version is going to run at 600 degrees. And we have in the reactor core, we have this very hot salt right next to the water, and we want the raw water at room temperature. So of course the water gets heated by the salt. So therefore we have to continuously cool the water. And for that we use commercially available air conditions.
Right. So we'll have a bank of these alongside in a gigawatt station.
Yeah, we would have 2 really big, even bigger than this one, really big air conditions for each reactor.
So our reactors are in 40-foot ice containers, same as what we're seeing now.
Yep.
Size and scale is the same.
Yeah.
Unfortunately, inside this loop, we can't see much inside because it's pretty dark and it's not open like you can see on this one. But can you give us a sneak peek of some of the stuff that might be in it?
Yeah, I mean, this is one is being built right now. It's not ready yet, but we have the reactor cores outside right now. Yeah, so let's go and have a look at that.
So this is a totally different design from what I kind of expected to see of maybe a molten salt pool reactor. Tell us about our reactor core.
Yeah, so this is definitely a very big innovation step for us in Copenhagen Atomic, but also for the whole world, because this type of reactor core is vastly more efficient than any other reactor out there that was developed in the past, and even the other advanced reactors that are currently being developed. The fuel efficiency of this one and the neutron economy is just much better than anything you've seen before. This type of reactor core is able to get 10 times more energy out of the same fuel that other reactors are using. So 10 times, when you say speed up, it's not speed up, but 10 times more efficiency out of fuel. That's really important.
So you said to me earlier when we did our practice runs, and let's be honest, we did do a practice run. The batteries didn't fail, by the way.
No.
But you said it's called the onion core.
Yes, so we've registered that as our trademark. It's called the onion core because it has many different layers, just like an onion, and it's sort of it's round a little bit like an onion. And in these different layers, we have salt and heavy water, and more salt and more heavy water, in a way where it's optimized. And we've been doing development of this for 7 years now. Lots of simulations, we've actually had to improve the simulation software to be able to simulate this.
So that design of the reactor core, combined with the approach we're taking of mass production of 40-foot ISO containers with all our reactors in, combined with how we're doing our full modularization, common parts, components, using commercially available, and if the commercially isn't available, then starting to develop for large scale, so like our Raspberry Pis, using those because we can effectively have mass production of these units, components, parts. And actually, if you look at our technology, it's fairly simple in terms of what it is. So scaling that up actually becomes far less risky. And that risk, that profile of modularization, the efficiency we're getting out of our reactor core, that's what's helping us get to 20 pounds per megawatt hour. Is there any other things maybe that contributing to that?
I think the most important thing is the new reactor core design. That's really what makes it possible for us to do energy at half of the price of what other competitors are providing. But also this mass manufacturing, when we can start to make one reactor every day, we can install 15 gigawatts of electricity per year. So it's on a completely different scale than Hinkley Point C or something like that.
Technically, we're saying 20 pounds per megawatt hour. We could do it for free, really. I mean, if we take the waste
technically that could be for free, right? So 30 gigawatt of electricity, which actually is giving UK economy free energy. So I think there's a lot of merit to how it is the approach that we're taking and the opportunity because of the design of this. But look, why don't we go back to the office and maybe we can take some questions. Okay, go on, Lolo.
Hi guys, can you hear me?
Hi. Yeah, we can hear you fine.
Brilliant. That was great. First of all, yeah, thank you for that tour. It's fascinating. And I think a real treat for us to see inside, kind of the inner workings of a company like Copenhagen Atomics doing kind of really big and important things. And just to reflect on what you kind of been saying already and where we are now with the UK. Obviously, the NIA is a UK trade body for nuclear, civil nuclear. And yesterday we had the budget, obviously, and big things. And one of the things that struck me just now was 15 gigawatts per year, one reactor a day and free power. I mean, if we can get to that point, that'll be absolutely brilliant.
Yeah, I think to get to free power, I might be pushing Thomas down a little bit too far. But technically, if we can use the waste, and I think the development of the technology, and actually, Thomas, you've got some salt here that you wanted to show them.
So those are the examples of the salt. We didn't see any salt in the factory. That's why I want to show now. So these are the salts that we're manufacturing. We used to do this in previous years, these ingots of roughly 1 kilogram of highly purified salt. But now we make salt in much bigger canisters of 100 and 200 kilograms per canister. And next year we're going to do 1 ton in each canister. So we're definitely moving forward with the salt production. This is the key to have purified salt is the key to reducing the corrosion. We have shown that you can easily run a reactor for 5 years in regular stainless steel with these salts without having excessive corrosion.
We've got some questions as well coming in thick and fast actually now. So I'll ask a couple. We've got one here from Joy. If you have water circulating close to the molten salt components, what sort of pressures are you needing to stop the water from boiling?
We have no pressure at all. The water is being pumped through really fast, and then we cool the water again. So the water come in at 5 degrees Celsius, and it comes out at the top at 25 degrees Celsius, and then it goes out through a cooling loop, and then it comes back in at 5 degrees. So no pressure on the water. It's there to moderate the neutrons, slow down the neutrons. That's the important thing.
And does the fuel salt need refueling, or the core is sealed for a number of years? That question from Mike.
Yes, the reactor is completely sealed for 5 years at a time, and then after 5 years we replace some of the components. And when we do that, we also load additional thorium salt. So it's sort of but it's not like a commercial light water reactor where you have to reload 20 or 40 tons of uranium fuel every 2 years. In this case here, we don't even have 20 tons of fuel salt at all. And we run it for 5 years, and then we replace, or we add an additional, 1 ton of, I think it's 800 kilograms of thorium every 5 years.
There's a question here from Moritz. Is there intention to commercialize the bespoke sensors and electronics? We obviously saw that this on the tour developed by you guys over there.
I mean, we already sell these test loops that we saw over in the factory to a number of universities, national lab, and when they get those, they also get all the sensors and all the valves and so on that come with that. We do not currently sell the sensors sort of on its own in a electronics market, but we have been thinking about it, and maybe sometime in the future.
Hopefully.
We're selling pumps, we're selling salts, we're selling test loops. I think the way in which we're commercializing the company as we go along is making our company quite robust. So maybe there's more products to be developed as we develop the technology further and further, right?
Yeah. So last year, obviously, to develop all this technology, we need lots of capital. So we take in capital from private investors, but last year we had sort of 75% of the capital expenditure was from investors, and the other 25% was from sale of these different components and molten salts and test systems.
there's obviously, you know, a journey to be had, and there's a road to get criticality by 2025, obviously, as you mentioned, and then technology readiness by 2028. Obviously, some very good things in the UK budget yesterday, announced by the Chancellor, labelling nuclear as green, for example, in the UK Green Taxonomy. There's a question here that is linked to this from Ben. You know, what do you see as one of the biggest challenges, or, you know, the biggest challenges to realising criticality by 2025 in the UK? You know, funding, supply chain, politics, for example. You know, there's a lot of things happening in the industry in the UK, exciting things as well. So yeah, what would the biggest challenges be, do you think?
I think the challenge for us right now is, you know, we've got to move from a water test to a FLENAC test to a thorium FLENAC to thorium fluoride test to a criticality test. So the challenge right now is, if we do a criticality test, we need to do that on a current licensed site, or we have to create a licensed site, and we need to have access to those. All of the licensed sites in the UK are all either government owned under UKAEA, NBA, or through the MOD. The other licensed site, which we could technically get hold of, I suppose, would be through EDF. But fundamentally, the difficulty is getting to a current and existing licensed site. So the challenge right now is, how do we get the criticality test? So we're looking for country partners that want to help us go through that criticality test. And the benefit for people like us in the UK is that we get to collaborate. We're a really open company. And now UK Atomics, which is what I'm kind of leading, is, you know, wanting to collaborate with people. We want to collaborate with countries, but that collaboration has to genuinely be collaborative, right? So, you know, what do we really need? What's the real challenge right now? It's to get a site to test our criticality test, right?
Yes, and we've said that we would really like to do that in the UK. The UK has a great legacy in the nuclear industry.
I mean, how many test reactors do we have in the UK, roughly? It's about 30 of, right?
Yeah, in the past, I don't think there are test reactors running now. Like,
no, not
yeah,
now.
in the past.
We might have one, or
yeah,
maybe two running in the UK right now. But, you know, in the past, we had zero power reactors, we had different technology test reactors, we had material reactors, we had a whole host of them at Harwell, at Winfrith, at Dounreay. So, you know, it's not uncommon for us to do it. It's just we haven't done it for a long time. So the challenge is, how do we get a site, and how do we work with the regulator to go through that kind of regulatory process, which actually we do new innovative technologies all the time in the UK, all the time, in decommissioning and in modification of plant. It's nothing new. So, you know, the real challenge is access to that site. I think the regulator will be on board with how we do it, as long as we work together and go through and validate, just like you would with any technology. The processes are there. It's really boiled back to access to site.
Yeah, we also have investors who say, you know, can we move on with this? How much is it going to cost? You know, can we run a criticality test for 20 million or 40 million pounds? And we go to the government and the regulator and ask, you know, what is it going to cost and how long is it going to take? And they don't really have the answers at this point. So we have to work together. And
siting is obviously huge. So I think the sound has dropped out there, Thomas, slightly. But siting is obviously a huge challenge. It has been for, you know, for a number of years in the UK. How do you foresee something like Great British Nuclear, this new government body? Do you think that's a good thing, a positive thing for the industry? And would it, I mean, potentially free up kind of sites for you guys and other developers as well?
So yeah, I think Great British Nuclear is really, really positive for the industry, and I fully endorse GB Nuclear being pulled and compiled and formed, and I can only see that as being a positive step for the nuclear industry in the UK. You know, how we deploy reactors, whether they be large scale gigawatt, whether they be light water reactors for SMRs, or whether they be, you know, our reactors for an AMR, actually there is a need for all of it. Whether we be looking at security of supply, the grid application, or whether it be security of supply and for heat application for industry, or energy, electricity for under private purchase agreements for industry, or whether it be to decarbonize, all of those need to be done. And doing that in a programmatic fashion is only sensible. It cannot be, the wrong thing to do. I guess the challenge is that you need to make sure that the market is open to technologies to develop at pace. And if you look at our program timeline that we had before, criticality test is in what's it now? I don't know why I look at my watch for the year, but 2 years. 2 years until we've got a criticality test, and that pushes us to being able to go to commercial in 5 years time, so 2028. And so you need to make sure that GB Nuclear has to facilitate that opportunity for people to have access to sites, for people to be able to develop at pace. And actually, under our current national policy statement and siting that's identified with the 8 different sites that are in the NPS, actually, GBN can help to identify new sites, new locations. And if you look at things like the reports that were done the other week and presented at one of the other conferences, one of the companies presented a whole host of new sites that we could do. So I think that's going to be needed to be pulled together, and GB Nuclear can only be positive with having somebody able to coordinate and facilitate pulling all those different departments together. So that's a real positive.
And there's a question linked to that, I would say, from Stuart here. What regulatory challenges do you anticipate, to permit use of these kind of plug and play units on sites not currently licensed for nuclear operations? Sites that may not be included in those kind of 8 sites, NPS sites.
Yeah, so plug and play is interesting because you would say that on a nuclear site you cannot do plug and play. I would challenge that massively. In the UK, we already do plug and play. You might not realise it, but we already do it. And companies are providing water treatment capabilities that come on the back of a lorry, come to the site, process some water, and then go back off of the nuclear site. It's a little different when we look at a nuclear reactor of plug and I'm going to say plug and operate rather than plug and play, because play sounds a little bit wrong with a nuclear reactor. We are most definitely building a nuclear reactor that's going to come off of a process line and be able to be fitted in relatively short, quick and simple, easy timeframes, i.e. we are genuinely taking it from factory off the back of a lorry, and then it's installed to connect to maybe the heat outlet, and maybe some electrical power inputs to be able to start it initially. But that's kind of it. It's fairly simple. So, the idea of plug and operate, I think, is absolutely essential. And we already have experience of doing it. A, in the water industry, B, in the nuclear industry, where we've brought these technologies to site. Magnox, modular active effluent treatment plant. It's a nuclear plant that was operated, run. It is ISO containers stacked on top of each other, for want of a better description, that is processing nuclear waste. Not like we haven't done it before, guys.
Exactly. And the question here for Thomas from Scott: given the corrosive salt environment and the need to keep fluorine gas dry, how are you addressing and minimizing the corrosion rate?
The main challenge in getting the corrosion down is to remove all moisture and all oxygen. Those are the most important things to remove. There are some other impurities in the salt when you get to fission products that you also want to remove, but the main thing is oxygen and moisture. And when you buy salt off the shelf from a chemical supplier, it has huge amounts of moisture in the crystals, and you usually buy these salt as powder, and that powder has a lot of moisture in it, because they're sucking moisture out of the air when you're transporting them and so on. So that's why you need to do a process to clean them before you can use them for nuclear purpose.
Great, interesting. Question from Ben, might be for Mike. In terms of the skill challenges in nuclear in the UK, will you partner with the utility, or is kind of, will it become more of an operation as a service? These might be kind of early questions to answer, but just in terms of kind of understanding how you might engage with the supply chain.
Yeah, I mean, it's a good question. We've been talking about this actually in the last 24 hours whilst I was here. So yeah, our model and what we're trying to do is to build, own, and operate and decommission our reactors, right? Mm-hmm. So typically that's kind of what a lot of the kind of conventional nuclear have been doing, right? Build, own, operate, and decommission. That's where they want to go. So that's not too dissimilar, really. But the difference that we're doing is because of the way in which our reactor is designed and intentionally designed, we can take the nuclear part of a nuclear site and we can move that boundary. So now we have the nuclear boundary where we build, own, operate, and take responsibility for the decommissioning. And we want to decommission because actually the fuel becomes a valuable part of our commercial model. And then the non-nuclear side, so this side over here, this can all be non-nuclear, standard balanced plant. And actually, if you think about it, it's kind of what we do in standard production for gas plants or coal-fired stations. We don't need to have, for our reactor design, we don't need to have a specialist nuclear turbine to fit to take certain types of high pressure water gases that are going to be turned into electricity and feed it back into the secondary loop. We have a non-nuclear salt, a solar salt at the moment, which is common, been used for what, 30 years of solar salts, where we transfer the heat through those solar salts to whatever application it is. So, the non-nuclear application can be grid, or the non-nuclear application can be an industrial application. So hydrogen production or ammonia production, whatever. The key point is we have salt coming out and we have salt going back in. That salt that comes out is completely non-nuclear. It's completely separated from that challenge. So we can draw the fence line at a different point with our technology. And that's why we are confident to say build, own, operate, and decommissioning. And when we say operate, how many people roughly might we need to operate just one?
Yes,
one reactor.
The molten salt reactors are different than classical light water reactors. They basically always load following. Mm-hmm. So the salt you talked about before, the nitrate salt that goes to the customer and delivers the heat, the amount of heat that the customer extracts from that salt. So the temperature that when it comes back, the temperature difference is basically what the reactor uses to determine how much power the reactor should produce. So the customer essentially, the amount of heat that they take out of the salt, that's what the reactor needs to produce again to keep running. So there is nobody in a control room trying to set levels of anything. It's completely automated. It's completely load following, and essentially there's only one thing you can do. You can stop the reactor. As an operator, you can press a stop button and then it'll shut down and go into decay heat mode. But there is nothing you could adjust.
That's great.
We don't need a lot of reactor operators.
Great. I think we'll have to leave it there, just given time. What I'd like to do is thank everybody who joined today's session. I think it was a fantastic insight into what the guys at Copenhagen Atomics, UK Atomics are doing. Very, very exciting. A lot of things on the horizon, obviously, and obviously thank you to Mike and Thomas as well. Any questions that we haven't been able to answer in the time today, we will send them to the guys, and they'll answer in their own time. And there's some really good questions we didn't get to. So without further ado, thank you very much for your time, and hopefully see you all soon. And yeah, good luck with everything, guys.